In episode 48, titled Univariate Analysis Narration, Distributions, Outliers, and Typical Behavior, the skill we build is the ability to describe one variable so clearly that a listener can picture it without seeing a chart. That matters on the exam because you will often be given a field description or a small summary table and asked what it implies about modeling, risk, or data quality. It also matters in real work because many audiences will never see your plots, and even when they do, they rely on your narration to understand what normal looks like. Univariate analysis is where you learn the personality of a variable, what is typical, what is rare, and what is suspicious. When you can narrate that personality precisely, you make better decisions about cleaning, transformations, and what claims the data can support. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A strong narration begins with center because center is how you answer the most basic question, what value is typical for this variable? The mean is useful when the distribution is roughly symmetric and not dominated by extreme values, because it summarizes the average experience in a way that matches intuition. The median is often better when the distribution is skewed, because it represents the midpoint observation and is resistant to a handful of extreme cases pulling the summary away from what most units experience. On the exam, choosing mean versus median is rarely about preference and almost always about skew and outliers, which is why this decision is such a common decision point. A useful narration states the center and also states why that measure is appropriate, because that shows you understand the distribution rather than parroting a statistic. When you start with center, you anchor the listener before you introduce variability and extremes. After center, you describe spread, because typical value without variability is a half-truth that can mislead decisions. Range gives an intuitive sense of the minimum and maximum, but it is sensitive to extremes and can exaggerate how variable most experiences are if a few rare values stretch the endpoints. Variance and standard deviation summarize average squared deviation around the mean, which can be useful when distributions are well behaved, but they can be unstable when heavy tails or outliers dominate. Interquartile intuition focuses on the middle half of the data, capturing how spread out typical cases are without being distorted by the extremes. A good narration ties spread to impact, such as whether most users experience similar performance or whether experiences vary widely, because that directly influences how you interpret average changes. The exam often tests whether you recognize when a variable is stable versus volatile, because volatility changes both modeling assumptions and operational decisions. Shape matters, and the simplest shape description starts with skew direction and what it implies about extremes. Right skew means a long tail to the right, where most observations cluster at lower values, but a minority take very large values, which is common in duration, latency, and cost fields. Left skew means the long tail is on the lower side, which can happen when values are bounded above and most observations sit near that bound. The implication of skew is practical. If a distribution is right skewed, the mean will tend to be larger than the median, and the average can describe a minority experience rather than the typical one. On the exam, skew is often a cue for both interpretation and modeling, because skewed variables may need transformations or robust summaries to avoid misleading conclusions. A clear narration states the skew direction and then explains what that means for the gap between typical cases and rare extremes.
Heavy tails deserve special attention because they are not the same thing as a few accidental outliers, and treating them as noise can erase meaningful structure.
A heavy-tailed distribution produces extreme values more frequently than a light-tailed distribution, which means rare events are a recurring feature of the process rather than isolated mistakes.
In security and operational data, heavy tails are common because many processes have bursts, spikes, and compound risk, such as incident counts, response times, and transaction volumes. The implication is that planning based only on average behavior will under-prepare you for frequent extremes, and models that assume thin tails may underestimate risk.
On the exam, heavy tails often justify robust methods, transformations, or alternative distributions because standard assumptions can produce overly confident conclusions.
When you narrate heavy tails, you're telling the listener that extremes are part of the system's normal behavior, not merely anomalies to discard.
Outliers are the points that stand out relative to the bulk of the distribution, but the most important skill is classifying what kind of outlier you are seeing. Some outliers are errors, like unit mismatches, parsing mistakes, impossible timestamps, or duplicated counts, and those should trigger cleaning rather than interpretation. Some outliers represent novelty, such as a new behavior pattern or a new attack technique, which should trigger investigation because it may signal change rather than noise. Some outliers are special cases that are valid but separate, such as a high-tier customer segment or a rare operational workflow, which may warrant segmentation rather than removal. The exam often tests whether you will reflexively delete outliers, because that is a common mistake, and the correct reasoning is to ask whether the outliers are plausible and meaningful given how the data is generated. A good narration states what makes the values outliers and then states what categories of explanation you would consider before acting. Percentiles are one of the most practical tools for describing service levels and experience differences because they let you talk about typical and extreme behavior in a way that maps to real decisions. The median tells you the 50% point, but percentiles like the 95th or 99th can describe what high-stress cases look like and what a tail user experiences. In performance contexts, percentiles often align with service-level objectives, where the goal is to ensure a high percentage of cases meet a threshold, not merely that the average looks good. Percentiles also help explain disparity, because two systems with similar means can have very different tail performance, and those tail differences can dominate user perception and operational load. The exam sometimes frames this as choosing a percentile-based metric to reflect user experience, which is a cue that tails matter more than averages. When you narrate percentiles, you translate a distribution into statements about how often people see good versus bad outcomes. When the variable is categorical, univariate narration shifts from numeric shape to composition, and the right summaries are counts, proportions, and missingness rates. Counts tell you how many cases fall into each category, while proportions let you compare categories fairly when total volumes differ across datasets or segments. Missingness rates matter because a category field with high missingness can distort downstream modeling and analysis, and missingness itself can be patterned, revealing measurement gaps. A strong narration describes concentration, such as whether one category dominates, because dominance can create imbalance issues and can also suggest that the field carries limited discriminating information. It also describes rarity, because rare categories can be important but unstable, especially if you attempt to learn separate behavior for categories with very few observations. The exam often tests whether you recognize when a categorical field is high cardinality, sparse, or heavily missing, because those properties influence encoding choices and model reliability. Checking for impossible values is a univariate habit that catches data quality defects before they contaminate every subsequent step. Impossible values include negative durations, percentages above 100, timestamps in the future relative to collection, counts that exceed physical capacity, and codes outside defined enumerations. The presence of impossible values is a signal about the pipeline, not just about the field, because it suggests broken validation, inconsistent units, or integration errors. On the exam, impossible values often appear as a clue that a dataset cannot be trusted without cleaning, and the correct answer frequently involves identifying the defect and choosing a remediation approach rather than interpreting the values as real. Even values that are technically possible can be operationally implausible, like a response time of 0 or a cost of 0, in contexts where that cannot happen, and those require the same skeptical attention. A careful narration explicitly states the bounds that should apply and whether the observed values violate those bounds. Transformations become relevant when scale or skew disrupts modeling, and univariate narration is where you justify them in plain language. A transformation does not change the underlying information, but it changes how the model sees differences, often compressing large values and expanding small values to make patterns more linear or more stable. Log transformations are common for right-skewed variables with heavy tails because they reduce the dominance of extreme values and can make relationships easier to model. Standardization, such as rescaling to comparable units, can matter when models are sensitive to scale or when distance-based methods would otherwise be dominated by one feature with large numeric magnitude. The exam often expects you to recognize when the raw scale is a modeling hazard, not because it is wrong, but because it can overwhelm learning and interpretation. A good narration states what problem the transformation solves, such as heavy skew, extreme dominance, or unstable variance. Robust summaries are another practical response when outliers dominate averages, because you want statistics that reflect the bulk of behavior without being hijacked by extremes. The median and interquartile range are robust because they are based on order rather than magnitude, which makes them stable even when a small fraction of observations are enormous. Trimmed means, where you remove a small percentage of extremes before averaging, can also provide a compromise between sensitivity and robustness, although the choice of trimming rate must be justified. The key idea is that robust summaries are not about ignoring important cases, but about preventing a few cases from misrepresenting what is typical, while still allowing you to analyze extremes explicitly when they matter. On the exam, robust choices often appear as the correct response to skew and outliers, especially when the question asks for typical behavior rather than tail risk. When you narrate robust summaries, you communicate that you are separating the story of the majority from the story of the extremes. At this point, the skill becomes storytelling, meaning you can tell a short, accurate story of typical and extreme behavior that connects center, spread, shape, and outliers to action. A good story might say that most observations cluster tightly around a modest value, suggesting stable, typical performance. But the right tail is heavy, indicating that extreme cases occur often enough to matter operationally. It might explain that the mean is higher than the median due to those extremes, so median and percentiles are better for describing user experience, while the tail should be analyzed separately for risk planning. It might flag a small set of impossible values that indicate a unit parsing defect, distinguishing those from valid high extremes that represent real bursts. The exam often expects this synthesis, because isolated facts about skew or variance are less useful than a coherent narrative that tells you what to trust, what to investigate, and what to model carefully. When you can narrate a variable this way, You have moved beyond computation into interpretation. A compact anchor memory for univariate narration is center, spread, shape, outliers, then action. Center tells you what is typical, spread tells you how variable it is, shape tells you how extremes behave, and outliers tell you what demands special handling. Action is where you decide whether to clean, transform, segment, or model differently based on what you observed, because univariate analysis is only valuable when it changes what you do next. The anchor also helps under exam pressure because it gives you a reliable order for thinking, and that order naturally maps to common question formats. If an answer choice jumps to action without evidence about shape or outliers, you can often eliminate it as premature. And if an answer choice describes numbers without suggesting implications, you can eliminate it as incomplete. The anchor is a checklist, but it is also a narrative structure, which is why it works for both exam answers and professional communication. To conclude episode 48, imagine describing one variable aloud and then proposing one cleaning step that is justified by the univariate evidence rather than by habit. Suppose the variable is session duration in seconds, and you narrate that the median is relatively low. Most sessions cluster near that typical value, but the distribution is strongly right-skewed with a heavy tail where a small but frequent minority of sessions last much longer. You would add that the mean is higher than the median because those long sessions pull it upward, so percentiles are better for describing user experience and service levels than the average alone. You might then note the presence of negative durations, which are impossible and indicate a timestamp ordering or parsing defect, distinguishing them from long durations that are plausible special cases. A reasonable cleaning step would be to correct or remove negative durations by fixing the underlying timestamp logic or filtering values that violate physical bounds, while preserving valid long durations for separate analysis of tail behavior. That is the essence of univariate narration, a clear picture of typical and extreme behavior, followed by a defensible action grounded in what the data actually shows. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.